Greetings and salutations, magical chemists. Let's talk about average atomic mass and mass spectroscopy. Mass spectroscopy, or spectrometry, either is acceptable, is what we use to measure the masses of elements and the percent abundances of their isotopes. The data produced from this type of experiment is called a mass spectrum. Luckily, you don't actually have to know how a mass spectrometer works, but you do need to know how to read a mass spectrum. In a given mass spectrum, like this example of silver, you will see multiple peaks, usually. The location of those peaks is what tells you the mass of that given isotope. The intensity of the peak, which is pretty much the height of the peak, that tells you the relative abundance. The higher the percent abundance, the more common that isotope is in nature. We can then take the information from a mass spectrum and use it to calculate the average atomic mass of a given element. Now, the average atomic mass calculation is a weighted average, so can't do it like a normal average. The formula is given like this. You take the mass of each isotope, multiplying it by its percent abundance of that isotope divided by 100, and then you just add them all together. But this is important. This formula is not on the formula chart. You just kind of have to know how to do this. Mathematically, it's important to note that the average atomic mass will be between the mass of the largest and the smallest isotopes. And in general, the average atomic mass is going to be closest to the mass of the most abundant isotope. Now, here's a fun story for you. It turns out the masses of a proton or a neutron are, well, they're approximately 1 atomic mass unit, 1 AMU, but the actual mass of each isotope is not a whole number. That's because of the nuclear binding energy required to hold all those protons and neutrons together in the nucleus. So the reason that matters is if they give you these specific, long, annoying, non-whole number masses to use for each isotope, you gotta use the specific non-whole number masses if they are provided. That's it for the theory. Let's try some tasty, tasty math problems. In our first problem, we're going to look at the 3 stable, naturally occurring isotopes of silicon. Silicon 28, 29, and 30. And so we give you their relative percent abundances, 92.21%, 4.70%, and 3.09% respectively. So before we actually calculate what its average atomic mass should be, I want to know, the weighted average, the average atomic mass, is that going to be closer to 28, 29, or 30? And why? You should totally try to answer this question, and then when you're ready to check your answer, unpause the video. In this case, we should predict that the average atomic mass will be closer to 28 because silicon 28 has the largest percent abundance by far, right? 92%. That's the vast majority of natural occurring silicon. All right, so now we're actually going to do the mathy math. To calculate the average atomic mass, all we need to do is to take the mass of each isotope and multiply it times its percent abundance divided by 100. And keep doing that for each of the isotopes. Now, I don't actually usually write this out this way because it seems like too much extra work. Instead, I'll usually write what I'm multiplying by after it's already divided by 100. And you can do whichever you want because they are equally mathematically valid. So mathematically, this is short and sweet. Just plug it into your calculator. Sig figs are a little annoying because of the sig figs, because we are both multiplying and adding. Then we actually need to stop and figure out what the answers are for each of these steps and worry about sig figs. It's going to be great. Because we're multiplying each of these things up above, we have to look at the least precise total number. Notice we can't use the whole number mass. That's given as a whole number, so let's treat it as an exact value. So I have 4 sig figs here. So if I was going to stop, I would have to stop at that place value with 4 total sig figs. So I use the total number of sig figs to determine the place value for each of the numbers that I'm adding together. And then I find the least precise of all of those, which ends up being just 2 numbers after the decimal. So that means my final answer has to be rounded to 2 numbers after the decimal. And don't forget to round up. And that's it. So let's try a couple more different practice problems on the next page, because there's a variety of different mathematical questions that can be asked about mass spectrometry and average atomic mass. This practice problem is very similar to the first one. However, please note, this time they gave us very specific, long, okay, maybe less pretty, but they gave us numbers that are very specific. They are not whole number masses, which means we cannot use the nice rounded whole number masses. These are the masses we have to use with our calculations. But other than that, nothing is different. So you should totally try this practice problem to make sure that the world makes sense. And when you are ready to check your answer, unpause the video. And here we go. Now, it is important to note, you don't actually have to show the second line that I'm writing out. I'm doing that for you. But you, if you were, doing a test, wanting to get a good grade, you would need to have that, and of course the answer with its units. So those are the two parts that are required to get full credit. All right, on to the next problem. So this problem is similar. However, instead of solving for the average atomic mass, which they give you, they want you to identify the mass of the second isotope of copper. We can still use the equation for average atomic mass, but now we're solving for a different variable. So let's plug in the information that we know. Now you might be thinking we've got a problem because we have two unknowns. We don't know the mass of the second isotope, but we also don't know its percent abundance. Well, we do know its percent abundance because they're saying that copper only has two isotopes, and we know the percent abundance of the first one, which means to find the percent abundance of the second one, we just have to subtract from 100. Since we were able to easily determine the missing percent abundance, now we just have a little bit of delightful algebra to solve for x, and that will give us the mass of the second isotope of copper. So you should totally try some tasty algebra, and when you're ready to check your work, go ahead and unpause the video. And that's it. You work out all the delicious algebra, you solve for x. The missing isotope of copper must have a mass of 64.91 AMU. All right, let's try a problem that actually has a mass spectrum in it, because those are ever so much fun. Also, there's something fun about some, not all, mass spectrum data. It is not always normalized. You notice in the previous problem, we were able to solve for the missing percent abundance because we assumed, well, there's only two isotopes, so they sure as heck better add up to 100%. Well, if you look at this problem, hey, look, there's only two isotopes, but they don't add up to 100%. In mass spectroscopy, the machine actually defaults to set the height of the highest peak as 100. So you can no longer do quite the same mathematical calculation when you're solving for the average atomic mass. Luckily, there's a really easy way to work with data like this that's not normalized. We're going to start the same way as always. You take the mass of the first isotope times its percent abundance. Normally, it'd be like, oh, it's 23%, so we're going to multiply by 0.23. But you can't, because it's not actually out of 100. You can't take 23 divided by 100. Instead, you're going to take 23 and divide by 123, because that's the combined total of all the percentages. So this is, in effect, normalizing our data. You just can't forget to do this step, otherwise you'll get some pretty crazy answers. But other than that, the math on this is the same. You're good, you use your calculator, the world loves you, and you get a delicious answer. In this case, the average atomic mass of boron is shown to be 10.8 AMU. All right, we have one more question type to look at, and it's a fun one. So we're going to go ahead and look at europium. And europium has two stable isotopes with the provided masses. And it even gives you the average atomic mass of europium, although to be fair, you could look it up on the periodic table. What they want you to do is to calculate the percentage of each of the two isotopes. What? Two unknowns? Kind of. But really, if you look at the hint, we're just going to set up a system of equations, and then the world will be our oyster. Or maybe the algebra will, I'm not sure. The first equation we need, of course, is the one for average atomic mass. And you'll notice I've just used x and y as my unknowns for each of the percent abundances, respectively. Now, the second equation, this is where you have to work back with the fact that we are going to assume, once again, unless you have that mass spectrum data that's weird, we're always going to assume normalized data. So in our case, x plus y have to equal 100%. But remember, we always take our 100% or our 25% and divide by 100. So we're going to say x plus y equal 1. So they're not in percentages anymore. So now we just need to solve for x or y, whatever we want to substitute for. And then we can plug back into our original equation and do lots of mathy math. So all I have to do now is do the algebra to solve for x, to find my percent abundance of the one isotope, and then plug into the second equation for x to solve for y, to find the percent abundance of the other isotope. I strongly advise you to try this math, because this is a more complicated problem type. That means it's more likely that the AP Chem people will give a problem to you, just like this one. So you should try this, and then when you're ready to check your answer, unpause the video. And there you have it, a tasty bit of algebra and your final percent abundances, which are actually pretty close to each other. And that is it. Thank you for playing with all the glories of delicious chemistry.